Hello, welcome to lab number 8. In lab number 8, we will investigate what happens when we have one-dimensional collisions. And one-dimensional collisions are going to give us an introduction to both Newton's third law, which we saw in lab number 7, and the concept of momentum and transferring of momentum. In this lab, we're going to explore forces of interaction between two objects and study the changes in motion that result in these interactions. We're especially interested in studying collisions and explosions in which interactions take place in very short periods of time. Now, early investigators spent a considerable amount of time trying to observe these collisions, but they encountered difficulties, not the least of which is the time intervals being so small, they literally happen in a blink of an eye. However, principles describing these collisions outcomes were well understood, and so they were able to make predictions that worked very well. So Isaac Newton used a concept of quantity of motion. We call that momentum. And so momentum is a property which involves it involves the motion of an object. So we're going to take a look at the collisions themselves. We'll start off with some simple collisions. In investigation number 1, we're going to talk about momentum and momentum change. All right? It's early fall. You're driving along a 2-lane highway in a rented moving van. It's full of your possessions, so you and a loaded truck and the loaded truck weigh 8,000 pounds. You've just slowed down to 15 miles an hour because you're in a business zone, and just as you pass through an intersection, you see a 2,000-pound sports car in the other lane heading straight for the intersection at 80 miles an hour and will never be able to stop. A desperate thought crosses your mind. You just have time to swing into the other lane and speed up a bit before making a head-on collision with the sports car. You want your truck and the sports car to crumple into a heap that sticks together and doesn't move. Can you keep the sports car from entering the intersection, or is this just a suicidal act? Now, to simulate this, what I'm going to do is I'm going to take 2 carts, and I'm going to change the masses of the carts, and I'll change the masses of the carts by adding masses to them. So each cart, this cart right here, is 250 grams, and the blue cart is also 250 grams. So to make the mass, make this equivalent of the red cart being the 8,000-pound mass and the blue cart being the 2,000-pound mass, I'm going to increase the mass of the cart. Each of these is 250 grams. And then I'm going to add one more mass, and that's going to give us a total mass of 1 kilogram for the cart. So here's our moving van of 1 kilogram. Here's our sports car of 250 grams. So there's our equivalents there. Prediction 1-1. How fast would you have to be going to completely stop the sports car? Explain your reasons for your predictions. And so I'm going to go ahead and try some head-on collisions in this short little distance. The sports car is going to be traveling fairly quickly. The moving van has got to be moving somewhat slower. So how fast do you think we're going to have to go? Well, let's see. I'm going to start off here, and I'm going to have the moving van move slowly. The sports car moves quickly. Let's try it again. Moving van moves slowly. Whoops, slowly. Looks like it stops pretty quickly there. What if I make the sports car move slower? Then the moving van is pushing the sports car back. Let me put my hands over here. You'll be able to see it better now. Okay, so moving van slowly. Sports car goes a little bit faster, pushes it back. Sports car and moving van move the same speed. The sports car gets pushed back by the moving van. And we'll do one more. Let's make the moving van go quick and the sports car move slow. And definitely the moving van is pushing bigger. So we have to impart a large amount of force. Let me try it again. Okay, slowly. So if we have a heavy object moving slowly, it can be stopped by a lighter object or less massive object moving quickly. So that leads us to question 1-1. What happens when the less massive cart is moving much faster than the more massive cart, much slower, or at an intermediate speed? So if the less massive cart is moving faster than the more massive cart, then it's possible for them to come to a stop. If the less massive cart, the blue cart, is moving slower than the large cart, than the red car, then we see that the red car pushes the blue car backwards. And we see that the blue car gets pushed backwards even at an intermediate speed. We see we've got to move the blue car very quickly in order for it to cancel out the motion, if you will, of the red car. Now, question 1-2, based on your prediction and your observations, what mathematical definition might you use to describe the momentum that you would need to stop an oncoming vehicle with a known mass and velocity? Should it depend on the mass, the velocity, or both? Explain your choice. So let's take a look at this. What we saw was the bigger the mass, you needed more. If we had two objects of different mass, then it seemed to be that the larger mass object had to have the slower velocity, and the lighter mass object had to have a bigger velocity. And if this quantity of momentum is a vector, then for them to be equal to each other, it seems to be that the mass and the velocity have to be inversely proportional. So this comes to our definition here. Just to double check your reasoning, you should have come to the conclusion that momentum is defined by the vector equation on page 179. Momentum P is defined as mass times velocity, where velocity is a vector and momentum is a vector, so momentum has direction. Okay, so now let's take a look at Newton's first two laws of motion. Every body continues in its state of rest or uniform motion in a right line unless it is compelled to change that state by forces impressed on it. And number two, the rate of change of motion is proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. That's a pretty fancy way, these are quotes basically from Newton's two laws. So let's translate this. What it means is, number one, an object in its motion will not change unless an external force acts on it. And number two, an object that has an external force acting on it will have a change in velocity proportional to the mass, or should be proportional to the force, and inversely proportional to the mass. Now, let's test the intuition about momentum and forces. You're sleeping in your room and your younger brother is making too much noise outside. So to keep the noise out, you want to close the door. But being lazy, the only way to close the door is to throw a super ball or a blob of clay at the door. The question becomes, which one is going to pack the bigger wallop? This is where we get at activity 1-2. Prediction 1-2. Assuming that the clay bob and the super ball have the same mass and you throw them with the same velocity, which one would you throw to close the door? The clay bob, which will stick to the door, or the super ball, which will bounce back at almost the same speed it had before it collided with the door? Give your reasonings for the choice using any notions that you already have, or any concepts developed in physics such as force, energy, momentum, or Newton's laws. If you think there's no difference, justify your answer. Remember, your life depends on it. Okay, so the question is, if we take a super ball and throw it up against the door, will it hit harder than if we take a clay ball, throw it with the same speed, and throw it up against the door? Remembering that the super ball is going to bounce off of the wall, so it's going to look something like this. Here's the wall. Okay. The super ball will come in, bounce off, and come back off. Whereas the clay ball will come in and it will stick to the door. So the question becomes, which one is going to exert a bigger force? The super ball or the clay ball? So what I'm going to do is I'm going to reset in order for us to do an experiment here. All right, now I'm going to do the experiment involving activity 1-2. Again, you had three possible outcomes. Either the clay ball is going to have a bigger force than the rubber ball, then the rubber ball is going to have a bigger force than the clay ball, or there will be no difference between the two. Okay, so what I'm going to do is I'm going to go ahead and do this experiment, which involves using the force sensor. We'll use this force sensor instead of the clay ball and rubber ball in order to measure the force that is being applied to bring the ball to a stop, or to however it's transferred. Okay. Now, we're going to do a number of experiments. The first thing we're going to do is we're going to take the mass of our force sensor, and the mass of our force sensor with the rubber stopper on the end of it is 100 grams. So we're going to go ahead and jot that down, 100 grams. Next, we're going to drop it from a standard height. And that standard height is going to be about the height of my fist right here. So I'm going to take a mark just so that I start at the same place each time. So there's the mark that I'm going to drop from. And let me go ahead and take my ruler here, measure the height, and the height is measured at about 9 centimeters. So let's go ahead and jot that down, that the height is 9 centimeters. So what's the force that is going to be transferred when the force sensor drops? Okay, so we'll put the force sensor here so that the stopper is right at 9 centimeters, and I'm going to drop it down like so. Now here's where we're going to have a little patience here, because unfortunately, ideally it should drop straight down. But because of this cable at the end of it, it may cause it to torque, and so what will happen is it may hit like this instead of hitting like this. So I'm going to go ahead and start recording. It is set so that it will not record the force until after a collision occurs. So hopefully, fingers crossed, I'll get it right the first time. So zero the force sensor. Let me put it vertically like that. I zero out the force sensor. That's going to zero out the weight of the rubber stopper. And let's do the experiment now. Okay, so we start recording. And we're going to place this, again, right at about 9 centimeters. And drop it. And that's a good data set. That is a perfect data set. And let's take a look. What we see is it looks like it took about 7/100ths of a second for the collision to occur. And what is the maximum force? Well, we can use our statistics function, select maximum, and we can see that the maximum amount of force needed was 54.4 newtons. So 54.4 newtons of force required to bring it to a stop. Okay. Now, let's replace the stopper with a clay ball. We want the whole thing to be about the same mass. We want the whole thing to be about 100 grams. So I'm going to freeze for a moment, and then I'll reset. I've replaced the rubber stopper now with a ball of clay at the very end of it. And I'm going to push it in place so that it's firmly into the clay holder that I have at the end. Again, I'm going to zero the force sensor, and let's see what happens. Again, I'm going to put the rubber ball about the same height. Again, 9 centimeters. And again, we're kind of eyeballing it, and I'm using the camera to kind of help me out there. All right, so let me get the mouse there, and let's see what happens. Okay, that didn't give me any data, so let's go ahead and delete that run and try it again. And there's also another possibility here. There's another possibility here that I haven't taken into account. So let's reset this. Zero the sensor. I'm going to bring it away from the whiteboard so that I can see it better. There we go. And again, we're going to drop it from about 9 centimeters. Okay. All right. Now it looks like we didn't get any data. But what I'm going to do is I'm going to repeat this, but I'm going to change the stop condition from 3/100ths of a second to 1/10 of a second. Okay. And hopefully we should be able to get a decent set of data as a result of that. Okay, so set it up again. All right, and okay, that time I could see what happened. I was looking at the experiment. What happened was it landed off to its side. So we're going to go ahead and repeat the experiment and see if I can land it onto the clay ball. Okay. We do not seem to be getting some data there. Let's try one more time. Let me do an experiment. I'm going to do a little test here just to see that it works. And I'm just going to slam it against the table. And it does work, but it's interesting how it took almost 0.8 of a second. So let's change the stop time again from 1/100th of a second to 2/100ths of a second and see if that allows more time for data to be collected. Okay, so one more time. Zero the sensor, place it above, place it at the right spot, and start recording it. There we go. We actually got a piece of data. I would be honest, to be honest, I'm not really that happy with it. I'm going to do one more experiment. Okay, so that one I was much happier with. And we see that the force, so we have a mass of 100 grams, we have a height of about 9 centimeters, and we had a force about 49.4 newtons. So somewhat less. Somewhat less. Now, there's a couple of reasons why. Especially, well, no, I'm not going to get into that. But there is somewhat less there. Okay, so question, now let's try one more thing. Let's take that small ball, leave that there, but this time instead of dropping it from 9 centimeters, let's go ahead and double the height, which means we want to put the line about another fist height, right about here. And let's see how much force is required to bring it to a stop. Right, so we'll zero the force sensor again, hit record, and let's see what happens. All right, that wasn't good data, so we're going to try it again. Tougher to do because the sensor wants to twist. So I actually have to counter the twist, if you will. Okay. Interesting. Not quite what I was expecting, to be perfectly honest. So we're going to do one more. All right. We end up getting a force. Let's go ahead and keep it at that. So we're going a mass of 100 grams for the small ball. This is the last line. A height of 18 centimeters. But now we have a somewhat larger force of 50.1 newtons. Now what happens if we have a larger ball? Well, to get a larger ball, that's not hard to do. I just happen to have a larger ball right here. The mass of the larger ball is 26 grams. The mass of the force sensor by itself is 92 grams. So now we're going to be looking at 180 118 grams. So 118 grams of this large ball. And I have to make it more pliable, I have to push it around on the desk here. All right. And we're going to drop this ball from the same height that we dropped in the first case. All right, so we're going to place this there at about 9 centimeters, and we'll go ahead and start recording. And let's see what happens. We got a whole mess of stuff, but we did get a maximum force. So 9 centimeters of height, and we have a maximum force of 54 newtons. So our conclusions here are that, so question 1-3, did your observations agree with your prediction? Which resulted in the maximum force, the stopper or the clay? So when the clay ball and the stopper ball, small ball, or rather the stopper and the clay had the same mass and dropped from the same height, the stopper exerted about 5 newtons more. 5 newtons more of force. Okay, and the reason why it was only 5 newtons more force, it actually should be more, is that this rubber stopper is not perfectly elastic. It doesn't bounce back like a super ball does. It does, however, bounce back. The real test of it is, for example, I drop it from 9 centimeters. It didn't come back up 9 centimeters. It just bounced a little bit and fell over. Now, when the next question then is, based on your observations, which should you throw at the door, the super ball or the clay ball? Would you use the super ball to exert the most force, or the clay ball to exert the most force? And it looks to me, from our diagrams here, that we will probably want to use the super ball. Prediction 1-3, what will happen to the maximum force if you increase the mass of the clay ball but allow it to drop with the same velocity? And it turns out that if we increase the mass, we increased the force. We increased the mass by almost 20 grams, and we got that additional 5 newtons of force. And then we also saw that if we doubled the height of the original ball, of the original small ball, that we had a little bit more force, not as significant as increasing the mass, but we certainly had an increase of 1 newton, or just about half a newton. So, question 1-5, did your observations agree with your predictions? What factor seems to determine the force exerted on the force probe? Okay, so the next step then is we need to talk about how to change momentum. It'd be nice to use Newton's formulation of the second law of motion to find collision forces, but it's difficult to measure the rate of change during the rapid collision without the special instruments. However, measuring the momentum of objects just before or after the collision is not difficult, because all you need to know is what's the velocity going into the collision versus what's the velocity coming out of the collision. So in the next activity, you're going to explore the mathematics of calculating momentum changes of 2 types of collisions. An elastic collision where we have a bounce, and an inelastic collision where we have a sticky collision. That leads us into activity 1-3. Which object undergoes the greater momentum change during the collision with a door? The clay ball or the super ball? Explain your reasoning. So what do you think? Which one is going to exert a bigger change in momentum? Okay. Now, in the comment, recall that change in momentum delta P is equal to Pi minus Pf. And I'm going to go ahead and jot notes. I'm going to go ahead and use this whiteboard here. So, and it's going to be a little awkward because of the way the whiteboard is set up. I don't want, actually what I can do, tell you what, let me go ahead and I'll set up the whiteboard behind the big whiteboard. So one moment here. Okay, so I'm going to go ahead and diagram things as we go along using the whiteboard here. We'll start off with a definition, recalling that momentum is listed as P, then we can write delta P is equal to PF minus PI. That is to say, the final momentum minus the initial momentum. Just like we did with change in position, just like we did with change in velocity. Now, to check your prediction with some calculations of momentum changes for both collisions you carried out. So let's take a look at one-dimensional vectors here. What we're looking at is, our diagram is essentially this. We have the floor right here. We have the ball starting at this point up here at some height, and it's going to drop some height, delta y, in the downward direction. The ball starts off with an initial velocity 0. It's going to strike the table, but it's going to have some velocity going in. Now this one velocity I'm going to call VI, or V1, and you'll see why in a moment. In the case of the super ball is going to have a velocity coming off, which I will call V2. So V1 going in, V2 coming out, and it'll eventually rise back up to a certain height. If V2 is the same as V1, then it should come back up to the same height. Okay. In the case of the clay ball, the final velocity is going to be 0, because in the case of the clay ball, the ball ends up sticking flat onto the surface, and so the final velocity V2 is going to be equal to 0. Okay, so step number 1, calculate the initial momentum of the clay ball plus the force probe just before it hits the table. So we're going to talk about the clay ball here. Now the clay ball, if you recall, had a mass m of 0.100 kilograms. Okay? 0.100 kilograms. The next step then is how fast is it going when it hits the table? Well, if you recall from our free fall equations, v squared equals v0 squared plus 2a delta y. Okay? So what we need to find out, we know free fall, we know the free fall acceleration. We need to find out what the height is. Well, I'm given the height. The height is going to be 9 centimeters. And so v0 being 0, since we're dropping it from rest, we get v is going to be equal to the square root of 2 times 9.8 meters per second squared times 0.09 meters. And that's where we're going to go with it. In fact, let's make the math a little bit easier. Well, no, we'll go ahead and use the math that we have here. So that's not a problem. Bringing in my handy dandy calculator, we get square root of 2 times 9.8 times 0.09 gives us a velocity v of 1.33 meters per second. So that's how fast it's going. And it's going in the negative direction because it's going downward. So I'm going to make it a minus 1.33 meters per second. Now the mass of the ball, as we said, was 0.01 kilograms. Since momentum P is equal to m times v, then the momentum of the ball, P, is going to be 0.100 kilograms multiplied by 1.33 meters per second. And so, obviously, the change is going to be the initial momentum, Pi, is going to be equal to, and that's going to be minus, is going to be equal to minus 0.133 kilogram meters per second. 0.133 kilogram meters per second. What is the step number 2? What is the final momentum? Well, the final momentum, PF, is going to be equal to 0 because the clay ball comes to a stop. It comes to a stop like that. It comes flat. So therefore, the change in momentum, delta P, is going to be equal to PF minus PI, or delta P is equal to 0 minus 0.133 kilogram meters per second, or plus 0.133 kilogram meters per second. Now that sounds kind of funny. Why do we have a positive change in momentum? Because the initial momentum is downward, the final momentum is 0. So if this is my 0 line, there's my initial momentum there, here's my final momentum here, so my change in momentum is this arrow right there. And that arrow is pointing upward. So there's my change in momentum. Okay, now let's take a look. What about the rubber ball? In the case of the rubber ball, let's assume that the rubber ball bounces back up to the same height it landed at. If it does, that means it had to have the same speed coming off the table that it had going in. That means that the velocity going in is minus 1.33 meters per second, but the velocity coming off is positive 1.33 meters per second. That means PF is going to be equal to the mass, 0.100 kilograms, multiplied by the velocity, which is plus 1.33 meters per second. And so that gives us, again, breaking out, we don't need to break out the calculator, just need to move the decimal place, and we end up getting positive 0.133 kilogram meters per second. This is PF. This is the final momentum. That leads us to the next question. Calculate the change in momentum of the stopper. To calculate the change in momentum of the stopper, again, PF minus PI. So it becomes delta P equals plus final momentum, 0.133 kilogram meters per second, minus the initial momentum, minus 0.133 kilogram meters per second. And so the change in momentum is going to be plus 0.266 kilogram meters per second. So what do we see? We see that when the super ball bounces, it actually gets twice the change in momentum. And again, that makes sense. If the initial momentum is pointing downward, here's PI, and the final momentum is pointing upward, here's PF, then the change in momentum has to be this vector right here. There's delta P. See? PI plus delta P gets us to PF. So that leads to question 1-6. Compare your calculated changes in momentum to your predictions. Do they agree? Which ball had the larger change in momentum? Question 1-7. How does the change in momentum seem to be related to the maximum force applied to the ball? Now that gets kind of interesting because it seems to be that we have a greater force applied to the rubber ball than we have to the clay ball. You've observed that the ball that bounces off the door will exert a larger maximum force on the door than the clay blob, which sticks to it. The ball that bounces off the door has a larger change in momentum because it reverses direction, while the clay blob doesn't. It just comes to rest. However, just looking at the maximum force exerted on the ball does not tell the whole story. Anybody who's ever done an egg toss at a field day knows what I'm talking about. If you want to catch an egg, it's not you have to catch the egg and you have to give. So in addition to applying a force, you have to apply a force over a period of time. In physics jargon, we would say in an official tone of voice that the egg and the hand have undergone an inelastic collision because they're stuck together. So what's the difference between catching the egg without give and catching the egg with give? Let's take a look at activity 1-4. If you catch an egg of a mass m that's heading towards your hand at a speed v, what magnitude momentum change will it undergo? Well, the answer is, well, let's see how we work that out. again, delta P equals PF minus PI. Okay? The initial momentum, PI, is going to be equal to whatever the egg was going at, whatever velocity the egg was going at, times its mass. So it's the mass of the egg times the velocity that the egg is moving at. The final momentum, PF, well, the final velocity is going to be 0. So the final momentum should be 0 as well. Therefore, delta P must equal 0 minus m times v, or delta P is equal to minus mv. That's the change in the momentum that has to be undergone. But what's the difference between catching the egg without give and catching the egg with a give? The answer is the amount of time it takes to come to a stop. Okay? Suppose the time you take to bring the egg is very big. Big delta T. Would you rather catch the egg in such a way that the delta T is big when you give? Or would you just catch it and just let it slam in your hand, where the delta T would end, the change in time would be very small? What do you suspect would happen to the average force when you're catching with a delta T very big? This is where we're going to get into another definition. On page 184, we have a definition called impulse, written as J. Impulse is defined as the force applied to an object multiplied by the time interval you apply that force. This impulse will cause the change in momentum. And so on a force versus time graph, we see that the area underneath the force versus time graph will give us an impulse. Because remember, force times time, anytime I have a product, I can represent that as an area. So if I have the height being force and the breadth being time, the area would give me the impulse, which would be equal to the change in momentum. Thus the reason why you want to roll with a punch instead of leaning into a punch. You get the same change in momentum, but if you roll with a punch, the time interval gets bigger, so the applied force gets smaller. If you go into the punch, the time interval gets smaller, which means the applied force gets bigger. At this point, I'm going to go ahead and stop, and that'll conclude investigation 1. I'm going to set up for investigation 2, where we will actually do a comparison between the impulse of a collision and the change in momentum of the objects.